In this video, I'm going to go through the OCR A-level chemistry paper. This is paper 1 from June 2018, periodic table elements and physical chemistry, the paper is called. Okay, so firstly, the multiple choice section. Okay, you've got a sample of boron, which contains the isotopes 10B and 11B, and the relative atomic mass is 10.8. Right, so we need to do this quite quickly. So rather than work it out from scratch, what I would suggest is, right, it's much closer, 10.8 is much closer to 11 than 10. So that means you've got a lot more of the 11 isotope. So that means it's got to be either C or D. I think it's C. Let's just try C. So the relative atomic mass then is going to be 80 over 100. So that's 0.8 multiplied by the mass of that one, which is 11. And the abundance of the other one has got to be 20%, 0.2 over 20 over 100. So that's 0.2. And the mass of that one is 10. So 0.2 times 10. So we get that, we get 8.8 plus 2, 10.8. So yeah, the answer was C. Right, now oxidation numbers, right? So we're going to use the sum of the oxidation numbers is equal to the charge on the species. Okay, so let's do the ICl2 first. Right, so is unknown. They tell us the chlorine is -2, and there's 2 of them, so that's -2 from the chlorines, and the charge on the species is equal to +1. So iodine, rearrange that bit of algebra, iodine is equal to +3. Okay, now the one Sb, which is antimony. So Sb, we don't know. The charge on that species is -1. We've got 6 chlorines, each one is -1, so that's -6 for them. So Sb is equal to +5. Okay, so 3 and 5, the answer is C. Okay, the next one then, we've got Avogadro constant question here. Number of hydrogen atoms in 0.215 moles of ethanol. Okay, so let's do the molecules of ethanol. And say molecules of ethanol is equal to the moles, 0.125, times the Avogadro constant. I'm just going to call it 6 times 10 to the 23. So that's going to give us, again, you don't have to work out the exact number because it's got, because you just have to choose an option, so save time, times 6 times 10 to the 23. That's 7.5 times 10 to the 22. And now we need to multiply that by 6 because you've got 6 hydrogen atoms in one molecule. So for the number of hydrogen atoms, it's 6 times that. Right, it's 4.5 times 10 to the 23. So it's that one there. Okay. Right, okay, barium hydroxide and nitric acid. So we have to remember they're going to react in, it's going to be barium hydroxide plus with 2 moles of nitric acid. Okay, to give you barium nitrate. Forming barium nitrate is that. Okay, won't complete the equation. So moles of barium nitrate, barium hydroxide, moles of that, conc times volume. So we've got 0.045 multiplied by 25 over 1,000. That gives us, let me see. Right, so that gives us so 0.045, 0.025, that 1.125 times 10 to the -3. Now the moles of nitric acid has got to be double that because it's a 1:2 ratio, yeah. Multiply that by 2. We get 2.25 times 10 to the minus 3. And finally, our concentration of nitric acid is equal to moles over vol. So 2.25 times 10 to the minus 3 divided by the volume, which is 23.35. So that's 0.02335. Gives us 0.96. It's this one here. Okay. So you have to know the equation, and then you have to just be able to do volume calculations. Okay. Right. Which statement explains best why nitrogen has a larger first ionization energy than oxygen? Okay, so remember it goes down for oxygen. Now the nitrogen, the electronic structure, nitrogen has got 2p, it's got 3, whereas oxygen is 2p4. And don't forget, nitrogen 7 in the periodic table, oxygen is 8. Okay, so if we look at the way the electrons are arranged in nitrogen, they are going to be unpaired, 3 unpaired electrons in the p shell. Oxygen, they have to start pairing up because there's more than 3. Right, so nitrogen atoms have less repulsion between p orbitals than oxygen atoms. That is the right answer, because when you're removing this electron from oxygen, it's paired up in the same orbital with another electron which will repel it, pair repulsion. Okay, this one, of course, just to check, nitrogen atoms, well, they do have a smaller nuclear charge, but you'd expect that to give a lower first ionization energy, so that's not right. Then neither of them are losing electrons from 2s, they're all coming from 2p. And D, I suppose you could, well, it's not right, is it? So 5a is definitely the best answer. Right, in the periodic table, X is in group 2, so that means it's going to form an X2 plus ion, and Y is in group 15 or 5, so 5 electrons in outer shell, so that's going to form a 3 minus ion. So that means the formula of the compound is going to be X3Y2. 6 is the right answer. Okay, which statement about ammonium carbonate is not correct? Right, it will form a precipitate with barium nitrate because you get barium carbonate is very insoluble. That's true. It will fizz with nitric acid because anything with a carbonate in, you add nitrate, you add hydrogen ions to that, you will get CO2. It will release NH3 gas, which is an alkaline gas, if you warm with NaOH, because what happens is you've got NH4 plus, and if you add OH minus, is a very good base. You remove a proton from that, form NH3 gas and water. And this one is wrong because the carbonate ion has got a 2 minus charge and the ammonium ion is 1 plus. So the correct formula is like that, isn't it? So not correct. D is the one that's not correct. So D is the answer. Orders of reaction. So rate concentration graph. So we've got rate on here and conc on that axis. It's first order, so it's directly proportional. So this is the right one. A is the right one. B is obviously wrong because the rate wouldn't decrease when the concentration goes higher. That would be a 0 order reaction for that one. For C, wouldn't it? 0 order. And this is this looks like a second order because it looks as though it's proportional to the concentration squared. Okay. So A is the answer there. Okay, sulfur dioxide and reacting with oxygen. Okay, so we want the partial pressure of SO3. So what we need to work out is the total number of moles. We need to work out the mole fraction. Mole fraction, which is usually, give the symbol lambda of SO3, is going to be equal to the moles of SO3 over the total moles. Right, the total moles is 2.4 plus 1.2 plus 0.4, which is equal to 4 exactly. The moles of SO3 we've got is 0.4. So the mole fraction of SO3 is equal to 0.1. Partial pressure is equal to the mole fraction of SO2 of anything, mole fraction of SO3 multiplied by the total pressure, big P. So that's going to be 0.1. Total pressure is 250 atmospheres, so it's 25 atmospheres is the answer to that. Okay, a buffer solution now. Right. So if you want to work out the pH of a buffer solution, the best thing to do is always to rearrange your Ka expression to get this. Okay, concentration of HA over the concentration of A minus the conjugate base. Right, now how many moles of HA have we got? Let's do moles HA in this mixture. We're going to work it out by concentration times volume. We've got concentration 2 and volume 0.2 dm cubed. 2 times 0.2 is equal to 0.4 moles. Okay, so the concentration of HA is going to be to the moles over the volume, and we're going to call the volume V. They will cancel out. Okay, so 0.4 over V. So we're going to put 0.4 over V into there. Now let's do the moles of A minus. Same thing again, concentration times volume, sodium propanoate. Okay, so A minus, we have got concentration 1 times 0.6 is equal to 0.6. So then we know that the concentration of A minus is equal to moles over volume, 0.6 over V. So we're going to put that into there. Okay, let's do that. So we get H plus is equal to the Ka, which is 1.32 times 10 to the minus 5 multiplied by 0.4 over V for HA, and for A minus 0.6 over V. Those V's are going to cancel out because they're both in the same volume, obviously. So we will do the maths there, and we get 1.32 exponential minus 5 multiplied by 0.4 over 6. That gives us 8.8 times 10 to the minus 6. As the hydrogen ion concentration, take a minus log of that to get the pH. Gives us 5.056. Okay, so that is it there. Okay, minus log of that is 5.06. So that's the answer there. Quite a lot of work there for 1 mark. Okay, entropies. Okay, entropy. So we want the entropy change for this reaction. Okay, so what we're going to do is the entropy is the sum of the entropies of the products minus the entropies of the reactants. Right, so the product we've got is methanol, so I'm going to write 239.7. So that's going to be equal to 239.7 minus, now the reactants, we've got 2 lots of H2. So I'm just going to, that's about 260. And carbon monoxide, 197. I'm not worrying about the decimal places because we don't have to work out the exact answer because we've got the alternatives there. So if you do that, you will find that that comes to about plus 219. So it's this one, sorry. It's minus 219, isn't it? Sorry about that. Bad mistake. Minus 219. Right, quick common sense check there. We've got a negative entropy change. Should we get a negative one? We should, because look, we have got On this side of the equation, we've got 3 moles of gas, and we're going to 1 mole of liquid on that side of the equation. So we definitely expect it to be negative. The entropy will be less disordered. So it's always worthwhile doing a common sense check. Right. Now, this looks like it's a lot of work, but if you know how a hydrogen oxygen fuel cell works, all that happens is hydrogen reacts with oxygen to form water. Okay, so you don't have to use the E cell values or anything here, or the equations actually. You just have to know that. So that is the answer. Sorry, it's not. This one is the answer. Okay, so you're using the energy you get out of that reaction to generate a current. If you really want to satisfy yourself that that's what's happening, well, you can see that the slow way of doing it is you can see that this one is the most positive, so that is going to be taking in electrons, so that means that's going to go forwards. And this one is the most negative, so this is going to be pushing out electrons, so that's going to go that way. Now, combine those two half equations together. You just have to add them because they're both 2 electron processes. And you'll see when you do that, that all those hydroxide ions will cancel out, and you'll just end up with, and one of the waters will cancel out as well. And you'll end up with this equation here. Which enthalpy changes are endothermic? Well, our definition of a bond enthalpy is the energy required to break a bond, so that is definitely endothermic. The second electron affinity of oxygen, that's also endothermic. You know that is going to be the case because you're sticking a negative electron onto something which is an oxide ion, which is already negative, so there's going to be repulsion there. So that was there. The standard enthalpy formation of any element in its standard state is obviously 0, so that's not endothermic. So 1 and 2 is the answer. Why reaction rate increases as temperature increases? Okay, now the activation energy is not less, it doesn't change, does it? It's the same. You do get more collisions between molecules, they're flying around faster, and this is true as well because a greater proportion of molecules have energy greater than the activation energy because the average speed of all the molecules goes up. They've got more kinetic energy. So 2 and 3 is the right answer there. Okay, this is a bit of recall, really. This one, this is cisplatin, isn't it? This stuff, this complex. This is cisplatin. One of its stereoisomers is used as an anti-cancer drug. It's the cis one. You're right. And just to remind you, all right, all right, I'll just draw it. So the cis means that the 2 chlorines are opposite each other and the 2 ammonia ligands are opposite each other. The shape you should know is square planar, so that is not right. The bond angles are going to be 90, and it doesn't have optical isomers, it has geometric isomers. So the answer is just 1, D. Okay, so what this question is about enthalpy changes. Okay, we've got hydration of fluoride ions. Okay, so explain what is meant by the term enthalpy change of hydration. That's 2 marks for that. Okay, so that is the enthalpy change occurring when 1 mole of gaseous atoms are dissolved in water. And it's going to be pretty exothermic because the polar water molecules are attracted to the charged ion and forms an interaction with it. Okay, for 2 marks that should be fine. Now I think I'm just going to scroll this up here. What we've got to do here is we're going to work out the enthalpy change of hydration of the fluoride ion using the energy changes in this table and the incomplete energy cycle below. So we've got to fill in on the dotted lines the species present. Right, now lattice enthalpy, let's have a look at this. This is when you form 1 mole of the solid lattice, so that's going to be CaF2 solid. And what do we form it from? The gaseous ions, so that's going to be Ca2 plus gas plus 2F minus gas. And then what's this going to be then? What's happening is we are, well, we're going to hydrate these ions. It's probably worthwhile looking at let's put the numbers in here. We don't have to till the next question, but it probably was going to help. That's going to be minus 1609. Now the solution, well, that is endothermic. So that means the arrow should be going up. So that's this arrow here. This is the plus 13. So what are we doing? So enthalpy of solution, we're getting 1 mole of solid calcium fluoride and we're dissolving it in water. So that is going to be Ca2 plus aqueous plus 2F minus aqueous. All right. So they've obviously done this in 2 stages here. So now we're going to hydrate the calcium and we're going to hydrate the 2 fluoride ions. Now you can see that they've made this arrow slightly bigger than the other one. So well, we don't know actually, so it doesn't matter which way around we put it. I'm going to hydrate the calcium first. So that's going to be it's going to be Ca2 plus Aq and 2F minus gas. So we haven't done anything to the fluoride ions in there. So that we're just hydrating the calcium. So that's minus 1609 here. And I'm going to call this X. Okay. So anyway, that's the first part. We've on the dotted lines, we've added the species present with their state symbols. And in the next bit of this question, it says, scroll down, calculate the enthalpy change of hydration of the fluoride ion. Well, look at X. What are we doing for X? We are hydrating 2 moles of fluoride ions here. We're going from 2F minus gas to 2F AQ. Right, let's work out so that's going to be X. Let's work out the value of X. So what we're going to do is I'm not going to worry about the signs, but I'm going to do this one. It's going to be 1609. I'm going to minus, sorry, I have to put the wrong number on there somewhere, haven't I? The lattice enthalpy 2630, sorry, that should be there. Minus 2630. So here that's going to be I'm going to do that number there. Okay, so all of that's 2630, and then I'm going to minus that much, minus 1609, and then I'm going to minus this much here. Don't worry about the sign, minus 13, and that is going to be equal to X, isn't it? Okay, that's why we draw a diagram, so you don't have to worry about the signs. And we know that X is, because the arrow is going down, that will be exothermic. Anyway, let's just get the number for it first. So that's 2630 minus 1609 and minus 13. That gives us X is equal to 1008. So that means the enthalpy of hydration of the fluoride ion is equal to half of that. So delta H hyd F minus is half of that, which is 504. And now I've got to think about the sign. Well, the arrow is going down there, so the sign is negative, and we know it's going to be exothermic anyway. So it's minus 504 kilojoules per mole. Okay. So we've done that. Carry on. All right, here's a bond enthalpy calculation. So fluorine reacts with steam as shown in the equation below, and the average bond enthalpies are shown there. Explain what is meant by the term average bond enthalpy. Well, I'm going to say bond enthalpy, first of all, is the energy required to break 1 mole of bonds. And the average bit, that means it's an average value taken from a range of compounds containing that bond. So there's your 2 marks there. Those two lines really, range of compounds. Right, now we've got to calculate the enthalpy of the fluoride of the FF bond. Okay, so we're going to have to draw a little energy cycle for that. Right, what I think I will do is I will paste that, get that equation there. Okay, so we've got that there. Now let's just think what bonds we've got in there. So we've got in the fluorine we've got single bonds. Okay, so we've got 2. So I'll draw it 2 times F, and we've got 2 times H2O. So we've got a total of 4 OH bonds there. And on this side of the equation, we have got a double bond between the oxygens, and we've got 4 lots of single bonds between hydrogen and fluorine. Okay, so what we're going to do is I'm going to say we're going to break all of those bonds. And so we're going to have the atoms here. So we're going to have 4 fluorine atoms, gaseous atoms. We're going to have 4 hydrogen atoms in the gaseous state, and we're going to have 2 oxygen atoms in the gaseous state, not joined together. And then we would join them back up together into the products. Right, so now let's look at the energy required to break that. So that is going to be 4 times 464. I'll do that in here. 4 times 464 for the hydrogen oxygen bonds, 4 of them, and we don't know what this is, so let's call that 2x. X is the bond enthalpy of the fluorine-fluorine bond, and on this one we're making 4 hydrogen fluoride bonds, so that's 4 times. Now I'm going to get minus because we're forming bonds, so that's exothermic. 5, 6, 8, 4 of them, and we're forming 1 oxygen double bond, which is minus 498. Add all that lot up together, that comes to minus 2,770, and add that lot together, that comes to plus 1,856 plus 2x. Now they give us the bond enthalpy, they give us the enthalpy change of this reaction. Delta H for this reaction is equal to minus 598. So Hess's law tells us then we are going to do, so I'm going to say that delta H minus 598 is equal to, well, going down this arrow here, so that's 1856. I'll put a plus in there to remind me, plus 2x, and then we're going up there, that's going to be minus 2,700. Okay, so just rearrange all of that. We get 2x is equal to that. Divide by 2x is equal to 158 kilojoules per mole. And that, of course, is the bond energy of the fluorine-fluorine bond. Okay, so that's that question done. So there is the bond enthalpy there, 158 kilojoules per mole. It's very easy to make mistakes in those sort of calculations. So do write a lot of it down like I've done, because if you make a mistake and your working's not clear, then it's very hard for them to give you intermediate errors, marks for working out. Okay, rate of reactions, question 17. Right, three ions react with iodide ions in this equation here. Okay, and we need to find out if they changed the concentrations of the two reactants here and worked out the initial rates. And what we've got to work out is the order of the reaction with respect to each component. Okay, so what I would do here is if we look at experiment 1 and 2. Okay, so this is a 6-mark question. Okay, so you've got to determine the rate constant, and we've got to determine the rate constant and suggest a possible two-step mechanism for the reaction that are consistent with these results. So I think we need to work out the orders with respect to things first of all. So let's look at experiment 1 and 2. Here, the iodide concentration is staying the same, but the ion concentration is doubling. It's going from 4 up to 8. And if we look at the rate of reaction there, what's happening? Well, it's going from 8.1 times 10 to the minus 4 to this. It's obviously doubling. It's going from 8 up to 16. So you double the ion concentration, you double the rate. So the reaction is first order with respect to the Fe3 plus ion. Now let's have a look at the iodide ion. Right, so which two experiments are we going to do there? We want to keep the ion concentration the same, so I'm going to look at experiment 1 and 3. Ion stays the same, but the iodide doubles. And when we double the iodide, you can see that the rate there goes up from 8.1 up to 32.4 effectively. Yeah, so it's going up by a factor of 4. So double the iodide, and you quadruple the rate, so it's second order with respect to iodide. You need to write that down as well, saying which experiments you are comparing. So the rate equation then is going to be equal to the rate constant multiplied by Fe3 to the power of 1 times by iodide to the power 2. Right, we need to work out the rate constant, so let's rearrange. You get K is equal to rate over Fe3 plus conc and I minus conc squared. Let's take the first line. Let's take it from experiment 1. Just put the numbers in there to work out K. So we're going to get the initial rate, 8.1 times 10 to the minus 4, divided by the ion concentration. That's 4 times 10 to the minus 2, 0.04. That's just to the power of 1, multiplied by the iodide concentration. So that's going to be 3 times 10 to the minus 2, that's 0.03 squared. Okay, let's put those numbers into the calculator and we'll get a value for K. Okay, that gives us 22.5 to 3 significant figures. And we need to state the units there as well. Right, so the units is going to be rate of reaction is mole per decimeter cubed per second. And we're going to have concentration mole per decimeter cubed per second, mole per decimeter cubed, right, to the power of 1 there, to the power of 2 there, that makes it to the power of 3. So that's equal to second to the minus 1 over mole dm to the minus 3 squared. So that's equal to second to the minus 1 over mole squared dm to the minus 6. bring that all onto the top line. The units are second to the -1 mole to the -2 dm to the 6. So we've worked out the rate constant. Okay, and we've done that. Now we've got to suggest a possible two-step mechanism that is consistent with these results. So what two-step mechanism? We're going to have one which is the rate determining step, the slow step, and then another one which is the fast step. Now the slow step, because it is first order with respect to Fe3 plus and second order with respect to that, we can presume that the slow step is the collision of one ion, Fe3 plus, with two iodides. That's what we can presume. Now, what's that going to do? Let's say the ion takes one of those electrons away, and we could end up with Fe2 plus, and that means we'd end up with I2. That would have a minus charge on it there. That would be the slow step. Now the fast step could then be the I2 minus is going to react with another Fe3 plus. That will give an electron to the ion. That's going to be Fe2 plus and leave behind an I2 molecule. That's one, and that's one suggestion for the fast. The slow step has really got to be that. There's only one alternative for that really. But then the fast step you can put, well, the first step, the slow step, you've got to have one ion reacting with two iodides. But there are slightly different things which, if you look in the mark scheme, they'll let you have, as long as you have this being the slow step with one ion reacting with two iodides, and then all your charges have got to be consistent and so forth. I think one of the other alternatives they had, instead of that, they made this a bit different. They said you get an Fe1 plus and I2, right? That would be consistent. And then the second step, Fe1 plus reacts with an Fe3 plus to give you two Fe2 pluses. So there were several different alternatives that are allowed there. Right. Now this is an Arrhenius equation question. Okay. So it carries out an investigation to find out EA and the pre-exponential factor A of a reaction. Okay, so we just write down the Arrhenius equation, the log form of it is probably the most useful. We'll write down ln K is equal to ln A is the pre-exponential factor, minus EA, which is the activation energy, over the gas constant R multiplied by 1 over T. Right, so they give you, they plotted ln K against 1 over T, and of course that is going to give us a gradient M will be minus the activation energy over the gas constant, the gradient of that line. So in the question then, what do they ask us to do? They ask us to draw a best fit line from those points that they were given there and calculate the activation energy from that. Okay, so how are we going to do that? We need to work out, so I've drawn the best fit line in green, and I've just drawn that yellow line as a sort of construction line to work out the gradient. So that's going to be delta X on that one. Let's go in yellow. It's going to be delta X, and this is going to be delta Y. I'll do it in blue. Right, so that's what is delta Y equal to? Changing Y, well, it's going to be, I make that 27.2. Minus, I make that 31.6 about there. So that's equal to minus 4.4. Let's work out the change in X. Is equal to, right, 5 times 10 to the minus 3. Don't forget your 10 to the minus 3 down there. Okay. 5 times 10 to the minus 3 minus, well, this here is 0. That's easy enough. That's 0. So that's 5 times 10 to the minus 3. Let's work out our gradient, M. M is equal to, change in Y, minus 4.4 over the change in X, 5 times 10 to the minus 3. That is equal to 880. Okay, now we need to work out EA. Well, we know that M is equal to minus EA over R. So EA is equal to minus M multiplied by R, the universal gas constant. R is equal to 8.31. This is important, joules per mole per Kelvin. So our answer for activation energy is going to be in joules, not kilojoules. So that's going to be equal to minus, oh, the gradient is minus, sorry. Minus 880, so let's make it a plus. Activation energy has got to be positive, times 8.31. And do that, that gives us 7,304 kilojoules, sorry, joules per mole. And we need the answer to three significant figures, so I should call that 730. Turn that into a 0 there. 7,300, that's the three significant figures. Okay, and joules per mole. Right, now the next bit of the question is going to ask us to work out the, says calculate the pre-exponential factor A, show you working. So we're going to, I'll do this here then, okay. So, right, we've just to write down the equation again, we get ln K is equal to ln A minus EA over R times 1 over T. Right, so what I'm going to do is I'm going to take a point on that graph. I can take one of the experiment. I'm going to take that point there, okay, on the line, and just substitute the numbers in. Right, what's the value of ln K there? Well, ln K is 27.2. So that's 27.2. Ln A we don't know, we're trying to find out. Minus EA over R, we worked that out before, is minus 880. So that's going to be plus 880, minus a minus, multiplied by 1 over T. Well, that's 5 times 10 to the minus 3. Right, so solve that. Just a bit of algebra. We get ln A, put those numbers in, is equal to 31.6. Okay. Right, so now we need to find out what A is. So A is equal to the anti-log of this number. So you do shift log on your calculator. So E to the power of 31.6, which is a very big number. It is 5.293 times 10 to the 13. That is the answer there. And they're fairly generous in terms of, like, if you know your gradient is always going to be a little bit different from the next person's. They're fairly generous as long as you draw a reasonable straight line, and the numbers fit in those boundaries, then you'll get all the marks. Okay. So, okay, that is that question. Right, so we found A. Yeah. Now is a question on equilibrium. Okay. So we've got this reaction between nitrogen monoxide, oxygen forming nitrogen dioxide. Write an expression for Kc for that. Well, Kc, pretty giveaway question, is going to be concentration of NO2 squared divided by the concentration of NO squared multiplied by the concentration of O2. Right. So we've got a chemist mixes together nitrogen, oxygen, and pressurized the gas, so the volume is 4 dm cubed. It's allowed to reach equilibrium, and at equilibrium, we've told the number of moles of nitrogen oxide and the moles of oxygen, and we're told the value of Kc, but we need to find out the number of moles of NO2. Right, so what I'm going to do is, first of all, I'm going to rearrange this equation, because we're going to be interested in the moles of NO2, so we want the concentration of NO2. So the concentration of NO2 squared is going to be equal to Kc multiplied by conc of NO squared multiplied by the concentration of oxygen. Now, concentration is equal to the moles over the volume, and the volume in this case is equal to, we're told, is 4 dm cubed, right? So I'm going to write down, I'm just going to leave that as concentration there. We know Kc is 45. Now the concentration of NO squared, well, the moles of NO is 0.4, so that's going to be 0.4 over 4, the volume, moles over volume, all squared, multiplied by the number of moles of oxygen we've got is 0.8, and the volume is 4 again, times 4. Right, so let's multiply all that out, and that comes to a nice even, nice round number of 0.09. If you put the numbers in your calculator, so we get NO2 squared concentration is equal to 0.09. So let's take the square root of that to get the concentration of NO2. That's equal to 0.3. Now we need to work out the moles of NO. Okay, so we know that moles is going to be equal to the concentration times the volume. The concentration we've just worked out is 0.3 and the volume is 4 dm cubed. So that's going to be equal to 1.2 moles. That's the answer. The number of moles of NO2 we've got is 1.2 moles. And you'd be surprised, but it's very easy to just mix up concentration for moles or mix up moles for concentration. They're not the same thing. Just most people who make mistakes will make mistakes as a result of that. So be clear in your head what's a concentration and what's a number of moles. Right. And then we've got a thing about Kp here. Okay, so the value of Kp for the equilibrium is shown at different temperatures. Okay, now just write down Kp for this is going to be equal to, it's more or less the same as so Kp is going to be the products, which is partial pressure of NO2 squared divided by the partial pressure of NO squared multiplied by the partial pressure of oxygen. Okay. Now look what happens when we increase the temperature, Kp gets smaller. So that means if Kp is smaller, we've got less of this at equilibrium, and we've got more of the reactants. Okay, so in other words, the equilibrium moves to the left. Now, that means the backward reaction must be exothermic. Sorry, it must be so right, let's see, when we increase the equilibrium goes that way. So we decrease the temperature, the backward reaction is exothermic because Le Chatelier tells us it's trying to warm it up by going in the exo direction. But it's actually asking for the forward reaction, so the backward's exo, the forward is endo. Okay, right. The chemist increases the pressure of the equilibrium mixture at the same temperature. Explain in terms of Kp, how would you expect the equilibrium position to change? Right now. Right, so we do a little bit more than just say the number of gas moles decreases. So I'm just going to copy the expression for Kp. I'm going to copy the equation down, okay? Let's just get the expression. Right. Okay, so there's our expression for Kp. Okay, now let's write down our equation. So we've got NO, 2NO plus oxygen going to 2NO2. Right, now we know that if we increase the pressure, the Kp doesn't change. That doesn't change, okay? But we have got two terms of gas on the top and 3 on the bottom. So that means if we increase the pressure to keep Kp the same, we have got to we've got to end up with a bigger number for the partial pressure of this one. So that's got to get bigger, and they've got to get smaller, and that's in order to keep Kp the same. So that means the equilibrium will move to the right. We're going to get more moles of NO2 and less moles of NO and O2. Okay, I will continue with the rest of that paper in the next video.